Recording. Okay, we're recording now. All right. So last time. So again, just to give you a quick reminder of what's going on. So remember, we're analyzing infinite series. Yes. There are only two types that we know exactly how to compute the sum. What are they?
Telescopic and geometric.
So geometric and telescopic, right? So remember the way we define convergence of a series is you look at the sequence of partial sums, right? That's Sn, which is a1 plus a2 all the way up to an, and then we figure out whether this sequence converges or not. If it converges, the series converges. If it diverges, the series diverges. Yes? Now, we can compute exactly what this converges to in the geometric and telescopic case. Now, the question is, can we determine convergence without having to compute the series itself? Because sometimes the sequence of partial sum is hard to understand. So then we talked about divergence test. What does divergence test says?
Says that if the limit of the series is equal to 0, then it may or may not converge, but if it's not equal to 0, then it definitely diverges.
Exactly, the limit of an, the general term of the series.
Limit.
If the limit of the general term is different than 0, then it diverges. Okay, if it's equal to 0, you don't know, it's inconclusive. Good. Then the next thing that we discussed was the integral test. What does the integral test says? If you look at the function that give you, just replace an by f of x by replacing n by x. If that function is positive, decreasing, and the limit is 0, right? Then the improper integral and the series, they have the same behavior, right? So we can bring everything from integration to analyze these problems. And therefore, we have the p series, which you get the same result as the p integrals, which is the p series is 1 over n to the p. When do they converge?
When p is greater than 1.
When p is bigger than 1 and diverge for p less than or equal than 1. Yes? That's what we have so far. And starting from that point on, everything we do is for series with positive terms. Okay? So this is very important. The an has to be positive. Then we talk about comparison tests. We did the direct comparison test and the limit comparison test. Okay? Just as a quick reminder, because now we're going to do examples of these. But basically, direct comparison test, you already have an idea of how this works when we talked about it in the case of integrals. And basically, the direct comparison test says if you have two series, okay, the series an and bn, you look at the sequences, and then if the sequence bn is always greater than or equal than an, then you have the following. If the series corresponding to the big one converges, then the small one has to converge. And the reason is because the sequence of partial sum of bn will be greater than or equal to the sequence of partial sum of an. If this converges, that sequence has a limit, therefore this is bounded, monotonic, so it has to converge. Okay? So that was the justification that we gave. Anyways, if the big one converges, then the small one has to converge, right? And similarly, an equivalent statement is if the small one diverges, then the big one has to diverge. Okay? So that's direct comparison test. But as you know, this typically is not a good thing to do. I mean, it is good. It's just that sometimes it's hard to establish that inequality. And we saw the example with this problem, right? The 1 over 2 plus square root of n that we needed to. I mean, we wanted to use square root of n, but it doesn't really work if you want to use direct comparison test, and you need it to be a little bit more clever, etc. So we introduced the limit comparison test, and okay, this thing here just went crazy. Not sure why. Why do you do this? Alright, so let me write it down again. So, what does the limit comparison test say? Remember, this is what we did on the board, and I just copied this from the previous notes that I had. But I guess there was a technical issue here. Okay, so then what does the limit comparison test says? I don't know if it was a clear.
It says that if the limit as n approaches infinity of the series an over bn or bn over an converges, no, is greater than 0, then the behaviors of the two series match.
Good. So limit comparison test. So you have two series, okay? So let AN and BN be two series and assume that when you take the limit as n approaches infinity of AN over BN, let's say that this is equal to L, is a number that's greater than 0, is a finite number, is a finite positive number, positive real number. Then remember, the discussion was that whenever this happens, there is actually an inequality working behind the scenes here, okay? You already have an inequality, and then we apply direct comparison test to that inequality that allows to deduce that whenever this happens, then the series AN and BN, they have the same behavior. Either both converge or both diverge, okay? So this makes this pretty simple. What you have to do is, given a series, find another series, so that when you take the limit, of course, the ones that you find, you need to know whether it already converges or not. So typically we use p-series and so on because you already know what's going to happen beforehand. You take the limit of the ratio of AN with BN. If that happens to be a number, then they have the same behavior. Okay? Either both converge or both diverge. And assume that this is L, is a finite positive real number, then either both series converge or both diverge. Okay? So they behave the same. Okay? So they have the same behavior. And we kind of did a couple of examples. The ones that are written here, we didn't do them. In fact, and that's the ones that I'm gonna do now. Okay? So we're gonna go over these problems, but let's start fresh. But they're already there, so that's fine. I'll probably come back and erase it, but that's okay. We basically did the example with the 1 over 2 plus square root of n, and then we compared with 1 over square root of n, and we showed that the limit was equal to 1, therefore they had the same behavior. And 1 over square root of n, that's a p-series with p less than 1, is 1/2, right? So it diverges, therefore our series diverges. Instead of having to get creative with an inequality or something like that. Okay, so then let's do a couple of problems in which we're going to be using this. So typically now you're going to find yourself using limit comparison test, because direct comparison test is a little bit involved, you know, like to do that inequality, it requires some argument, and why do that if you can use limit comparison test? We already have it, so let's use it, okay?
So are there any scenarios that when we need to compare two series, the limit comparison won't work, then we'll have to use
well, if you get 0 or infinity in that limit, then it doesn't work. You have to do something else.
Okay.
Remember, limit comparison test is when you take the limit, you get a number,
Right.
positive number.
So if we get like 0 or infinity, then we would have to do the direct comparison.
Direct comparison or something else.
Okay.
So in 5.6, and then in 5.6, you're going to learn another technique that may help you figure out convergence. Okay? All right, so determine convergence, if possible. I mean, maybe at this point with our knowledge, there will be a problem which we need to say inconclusive. Okay? All right, so let's see, let's do the sum from 2 to infinity of 1 over 3n squared minus 4n plus 5. Let's do the sum from 1 to infinity of the square root of n over n squared plus 1. And then let's take a look at n times 2 to the n over 4n cubed plus 1. Okay, so here we have three series. Let's try to determine whether they converge or diverge. So remember, these theorems that we're talking about, they only work when the terms of the series are all positive, okay? Which in this case, they are positive, okay? So we're fine. But, yeah, we're fine. when they become negative, etc., what we're doing doesn't work. That's why we're gonna be doing all the stuff in 5.5 and 5.6 is so we can deal with series that are not positive. Okay. All right. So let's do this. The first one, solution. What's the first thing that you should do when you look at a series?
Limit.
You need to take the limit. You should take the limit. So divergence test, because if the limit is different than 0, you stop immediately and you say divergence and move on. Okay. Now, if you look at this one, the limit is clearly 0, right? So you don't even need to write it. Just look at it, and then you can tell. So this one, the limit is 0, so we're gonna move on. Now remember, this is a rational function. I explained to you last time that when you have a rational expression, rational expression here, and you want to use limit comparison, you will use a p series. The question is, what is p? So what should be p in this case? P equals 2. Good. Remember, p is going to be the overall degree of your expression. You just need to subtract top minus bottom. But if you want bottom minus top, because typically, if you get to that point, it's because the degree of the top is less than the bottom. Because otherwise, this limit will not be 0. And then you already know the divergence. Okay? So if you're going to compare with a p series, it's because the degree of the top is less than the bottom. So this guy is bigger. So if you want, you do bottom minus top. If you do top minus bottom, you get a negative number. So 2 minus 0 is 2. So here you should be comparing with a p series with p equals 2. So compare. I'm going to use limit comparison with the sum from 2 to infinity of 1 over n squared. Yes? And let's just put here already. What do we know about this? Converges or diverges? Converges. So this is a series that converges. And the reason is, it's a p series with p equals 2, which is bigger than 1. Okay? So all that is left now is to take the limit and see if we get a number. If we get a number, then that means that our series will converge as well. Okay? The number, a positive number. Okay. So let's take the limit. Limit as n approaches infinity of 1 over. It doesn't matter which one you put on top or which one you put in the bottom. Okay? We're going to do it like this. So this will be limit as n approaches infinity. Remember, when this happens, you multiply and you flip the second fraction. So this n squared goes straight to the top. So it becomes n squared over 3n squared minus 4n plus 5. And what is this limit?
1 over 3.
That's 1 over 3. Degrees are the same. So that's why we picked p equals 2. So at this point, we get the same degree. So we can just do the ratio of the leading coefficients. That's the reason why we're picking p equals 2. If you pick any other p, you put any other number here. If you put 5, you're going to have a 5 here. This limit will be infinity. If you put 1, you're going to have a 1 here. This limit will be 0. Okay? You want it, so the limit is a number. The question is, can you find a p that makes this work? Yes, with p equals 2, it works. Okay? And the trick is the little overall degree that it makes. Okay? Everybody understand this? So it's equal to 1 over 3. The point is that it's a positive number. So what can we deduce?
1 over 3n squared minus 4n plus 5, or the series converges.
Okay, so
Yeah.
the series converges. So by the limit comparison test, our series converges. Why? Because we know that the other one converges, and because they behave the same, then this one has to converge. Do you understand this? Questions? All right, let's take a look at the next one. How about sum from 1 to infinity of square root of n over n squared plus 1? Once again, the degree of the bottom is bigger, so when you take the limit, this will be 0. Okay? The bottom grows faster. So, what should we use?
1 over n to the 3 over 2.
So, how do you get 3 over 2? What do you do?
Subtracting the 2 on the bottom by the 1 half on top.
Right? So, you see this? This looks like a rational expression. It's not really rational because it's radical, but again, as I mentioned, include the radical in your considerations here. So you should be comparing with a p series What P series? Well, the P would be the difference of the degrees. Degree of the top degree is 1/2. This is 2, so 2 minus 1/2 is 3/2, right? Or 1.5. So point is that here we compare, so limit comparison test with 1 over n to the 3/2. Yes? What do we know about this one?
Convergence.
So we know that this one converges because it's a P series with P equals to 3/2, which is bigger than 1. So all that is left now is to take the limit. One over n to the 3/2. So it would be limit as n approaches infinity. Now to make it easier, n to the 3. So the n to the 3/2 comes to the top. I'm gonna write it as square root of n cubed. Yes? So that means that's square root of n cubed times square root of n over n squared plus 1. And I did that so that you can multiply. So you're gonna get square root of n to the 4, which is n squared, right? And what is the limit?
1.
Is equal to 1. Once again, what you care about is that it's positive. Okay? It's a number, it's positive. So again, by limit comparison test, we have that our series converges. Questions? Do you understand this? All right. Now let's take a look at the last one. So we have n times 2 to the n over 4n cubed plus 1. So sum from 1 to infinity of n times 2 to the n over 4n cubed plus 1. So here you cannot use the logic that we're using above about the overall degree and whatnot, because this is not a rational expression per se, because you have this 2 to the n, you have this exponential here. Now what can you say about this series?
It diverges.
Why?
Because the limit of it does not equal 0.
Good, can you tell me what it is?
It's infinity.
Infinity. The top grows like crazy, right? Exponential grows way faster than polynomial. So when you take the limit as n approaches infinity, this is going to be positive infinity. Okay? So it diverges. Now, if we still wanted to instead of doing that, so okay, so let me just write it down, but I'm going to use limit comparison test also just to practice. And let's just say note. If I go ahead and take the limit, this is positive infinity, which is certainly, different than 0. So by the divergence test, the series diverges. And then that's it, you're done. Okay? You're done. Now, if you want to, because technically then you need to argue why this limit is positive, and we say here because this goes faster, but in reality, you will need to use L'Hopital's rule, right? And then there will be a product rule involved in the top, and all of that business. So if you don't want to go through that process of computing that limit to justify why you're saying that, then let's exchange that for something easier. So alternative would be to consider the following: 2 to the n. So this product is really what's in the way, and this plus 1 is really what's in the way. So I'm going to go ahead and consider 2 to the n over n squared, because if we didn't have this plus 1, this n would cancel with the n cubed, and you have an n squared, right? Remember, at infinity, this plus 1 is irrelevant, so you can ignore it if you will. So this is going to behave like 2 to the n over 4n squared. Okay? I don't care about the 4 either, I just care about the stuff that has the variable in it. So that's the reason why I'm writing n squared. Now this is a limit that you can, in one shot, quickly show that this limit is infinity. There's no need to do product rule, nothing like that when you use L'Hopital's rule. So This is, I guess, even it's also clear that this diverges since I'm gonna write like this. So this will be the same as limit as x approaches infinity using L'Hopital's rule. This is 2 to the x times ln of 2 over 2x. Then you do it again. Again, if we went this route, it's because we wanted to justify completely. Okay. So when you take derivative of the top, you keep getting your exponential. It's just that this guy start getting some power. But at this point, you have a 2 in the bottom. So then this is just positive infinity. Okay. So diverges, I will say here, by divergence test, since the limit is different than 0. And then, why am I considering that one? Because when we take the limit of our series with this one, let's see what we get. So limit as n approaches infinity. I'm expecting to get a number because, as I said, this guy behaves the same as this one. Okay, we obtain this one by removing the +1 and ignoring the 4. Okay, so I'm expecting to get a number in this limit. So let's see, what is it? So n 2 to the n over 4n cubed plus 1 times n squared over 2 to the n. This cancels. So you get limit as n approaches infinity of n cubed on top over 4 n cubed plus 1 in the bottom. What is this limit? That's 1 over 4. It's greater than 0, right? So what does this mean by limit comparison test? That these two series behave the same. Because we already know that this one diverges, then our series diverges. And again, it's simpler to just use the divergence test originally, but then you will need to carefully compute that limit, take product rule, and all of that. Okay? But you can also use limit comparison test, and I'm using it just to show you that it doesn't have to be just with a p-series. Okay? You can use limit comparison test with whatever you want, as long as it works. Okay? So by limit comparison test, since we already argued that this guy diverges, then the original series four n cubed plus 1 diverges. Okay? So I guess the point here is that you don't have to use limit comparison test with a p series only. You can use it with any other series. Okay? As long as everybody is positive and the limit is a number greater than 0, they will behave the same. Okay? All right. But I repeat, if this was the problem, I would just do what I did in red and stop right there. It's simple. Okay? But if you have issues showing these down or explaining something here, then you will want to consider the body. Okay? Yes.
So on the test, can we do just what's in red because the top grows so much faster?
You tell me that, and then I'll buy. Okay. But you need to understand that there could be people that say, "What do you mean?" And then you have to explain. So as long as you understand that, then that's fine. Okay. Questions about using limit comparison test? Do you understand how to use it? Okay, so remember, this only works when the series is of positive terms. Okay, so now we already have several techniques to deal with series with positive terms, but what if we don't have positive terms, okay? So what do we do when we start getting negative terms in the mix? And first of all, if everybody's positive, then that's not a big deal because you can factor out a -1, making everybody positive. I mean, if everybody's negative, you factor out -1, makes everybody positive, and you analyze that series. If that one converges, then the original series will converge because the property of multiplication by a constant. Okay? So the next case is, what if sometimes it's positive, sometimes it's negative? And the easier case in that category would be alternating. Positive, negative, positive, negative, positive, negative. Why? Because we'll be able to control what happens in that case. Okay? And then explain how we do it. So that's the next section, which is what we call alternating series. Okay? So let me define, I mean, the name is kind of already very suggestive, but anyways, let me write it down. So definition, a series is called alternating if its terms, if the sign of its terms alternates between positive and negative is important in a consecutive way. In other words, positive, negative, not two positive, then three negative, then two positive, three negative. No, positive, negative, positive, negative. Okay, that's what I mean in a consecutive way. In a consecutive way. In other words, so equivalently, a series alternating if the general term. So how do you take care of the alternating behavior? How do you write positive 1, negative 1, positive 1, negative 1? How do you write that? Negative 1 to the n, where n is something that's increasing. When n is even, you get positive. When n is odd, you get negative, right? Now, sometimes we have negative 1 to the n or negative 1 to the n plus 1. And that depends on when you are starting. Okay, for example, let's say that you start at 1 with your series, but you want to have a positive, the first term to be positive. You don't write negative 1 to the n, because then when you start with n equals 1, you get a negative. So you write negative 1 to the n plus 1. Okay? So a series called alternating. So if it has the form, or if it can be written in the form negative 1 to the n times an, or negative 1 to the n plus 1 times an. And I mean, it doesn't really matter where it begins, okay? It can begin at 1, at 2, at 20, it doesn't matter, okay? The point is that you spot the alternating behavior when you see this. Now, you have to be careful here. So, I guess, example. Determine if the series is alternating. So we just need to say yes or no, okay? So I'm gonna write here the sum, let's say from 1 to infinity of negative 1 to the n plus 1 or 1 over n. And I'm gonna write here the sum from 0 to infinity of sine of n pi over 2 over n squared plus 1, the sum from 0 to infinity of cosine of say 2n plus 1 pi or square root of n, whatever. So 1, no, let's make it simple. Let's just say n pi. Okay, and then the sum from 1 to infinity of negative 1 to n times n plus 1 is equal to n squared. Times 1 over n. Again, I'm just making up some examples here. The point is, I want to make sure that you recognize where the series is alternating or not. Okay. In the homework, there's an interesting one also. Anyways, let's see. The first one. What do you think? Is it alternating?
Yes.
Why?
Because there's the -1 to the n plus 1.
Okay. Okay. Good. And what I want you to understand is, for example, what do you think about this one? Is this alternating?
No, it's always the odd.
It's always increasing.
This is always odd.
Yeah,
Right.
so it'll always be negative.
So this is always odd, so this is always -1. So this is actually negative. So the answer here is no. And then let me give you this. How about this one? That was the original one that I have written down, but then how about this one? Oops. Well, okay, if you have this,
No. this is
no,
always
because then
negative.
everybody will be positive, right? How about this? No, it's a little bit more tricky, but this is alternating.
No,
No,
no, it's not.
because that can be
It's
even more
not.
odd, so.
Yeah, it's-
So let's see. So I encourage you to write down examples first, like the first few terms to see what's going on. For example, when n is 1,
It is negative.
it's negative. When n is 2,
It's positive.
it's positive. When n is 3,
Negative.
Oh,
it's
yeah.
negative.
It will change.
The point is that when you square an even number, you still get even. But when you square an odd number, you still get odd. So this is alternating. So what I want to tell you is, maybe it doesn't look like that, and it will be alternating. Okay, so you have to be careful. Okay, so point is that this you can rewrite it as this. Because when n is odd, n squared is also. So here what you care about really is the parity of n to determine the positive or the negative, right? Whether it's even or odd. And the parity of n is the same as the parity of n squared. Okay? So you can erase this and put -1 to the end. Okay? So this one is a yes, it's alternating. Now this one is also yes. And the point is, for you to get alternating is the fact that the power of the -1, it has to be consecutive numbers, or at least numbers that alternate between even, odd, even, odd, even, odd. That's how you get your alternating behavior. Okay, so just keep that in mind. How about B?
No.
Why?
Because 1, 0, -1, 0, 1, 0.
Very good. So here n is just integer. So what do you get here? So sometimes, let's see, if you get a multiple of pi, if you get an even number, you're gonna get 0, right? When n is even, you get sign of a multiple of pi, because the n cancels with the 2. So you're gonna have a 0. So this would be 0. And then when n is odd, this would be either at the pi over 2. Think about the unit circle. It would be either a multiple of pi over 2 or a multiple of 3 pi over 2. Yes? So it would be either 1 or -1. Do you understand this? And then, so it alternates. Because the zeros you get, you remove them.
Oh.
So, right? The zeros, you remove them. So, yeah, this one is tricky. But yeah, the zeros, you remove them. So basically, the point is that this is the same thing as when n is even, these terms are 0. So this is really just an odd, right? It's the same thing as adding this expression when n is odd. And then when n is odd, what can we say about this? So in other words, our counter is just going from 1, 3, 5, 7, etc. Because anyway, the even guys, they will give you 0. Yes? So when n is odd, what happens here? When n is 1, you get 1. When n is 3, you get -1. Then 5, you're back to 1. Then 6, then 7, you're back to -1 because you are coterminal with 3 pi over 2. So this is the same thing as, so we start with a positive. This is actually the same thing as n. Now all n's. This one is a little bit harder. My apologies, but that's okay. So we start positive. So I started at 0, so I'm gonna do -1 to the n. Now we need to change the series completely. And you ask me questions once I finish writing this down. Ask me questions if you understand. So first of all, do you understand this equality? That this thing is equal to this. You see why I said odd? Because when n is even, this top will be 0 because you're gonna get a multiple of pi here. So that term doesn't matter. So the only term to survive here is when n is odd. So we have this. Now I want to go back and I want to have a series, so I need my series to start at 0 and be 0, 1, 2, 3, 4, 5, etc. I don't like this. So that means that we need to modify. If I change from odd to all the numbers, then I need to modify this expression. Because when this is just when n is odd, this guy we already know this is 1, -1, 1, -1. So I just want to write -1 to the n. And because we start at 0, then this -1 to the n takes care of the numerator. Agree? That's going to give me my +1, my -1, my +1, my -1. Now we need to modify this. Because when you write the terms, what is it that you're plugging in here? Odd numbers, right? So you first put a 1, then you put a 3, then you put a 5, and so on. So how do you write odd numbers when the counter is 1, 2, 3, 4, 5, etc.? 2n plus 1. So that would be 2n plus 1 squared plus 1. So that series is the same as this series. Okay? So again, if you write down the terms, you will understand it better. So what are the terms of the original series? When n is equal to 0, what do we get?
0.
We get 0. When n is equal to 1, what do we get?
1/2.
Then we get 1/2. When n is equal to 2, what do we get? 0. When n is equal to 3, -1 over 10, right? Because it's 3 squared plus 1. When n is equal to 4, 0. I'm going to do one more. When n is equal to 5,
126.
so we are positive because 5 pi over 2 is coterminal with pi over 2, right? So it will be positive, and then it will be 1 over 26, and so on, right? So ignore the zeros, and you're going to get this one over here. What's the first term here? Remember, n is odd, so that means n is 1, 3, 5, 7, okay? So what's the first term in here?
1/2.
It will be 1/2. Then when n is equal to 3, -1/10. When n is equal to 5, plus 1 over 26, and so on. So this is just what we had above, but without the zeros. Do you understand this? Now let's see what is this. What is this? When n is equal to 0.
1/2.
So when you put 0, that's positive, and then you're going to have 1 plus 1, right? That's 1/2. Then when n is equal to 1, you get a negative. Then what happens when you plug in 1?
You get 3
You
squared.
get 3 squared plus 1. That's your 10. Then comes a positive. So that's 2. So for n equals 2, what do we get? That's 5 squared. That's your 26. And so on. So these three expressions that you see here, they represent the same infinite sum. It's a different way of writing those. It's just that if we want to study this, we need to have a counter that's that looks like this: 0, 1, 2, 3, 4, 5. Because we haven't studied how to deal with this kind of stuff. You can play this trick. You can switch if your counter is only over the odd numbers. You can switch it to be over all the numbers, but then you need to modify the expression inside accordingly. Okay? If it would have been over the even numbers, then you modify the expression inside by replacing n by 2n. Okay? Because that's how you write even numbers, right? 2 times an integer. Odd numbers, 2 times an integer plus 1. Okay. And the thing is that these things are done a lot. I could have done it like this also. I could have begun with 1, but then to fix it, what do I need to do? To put a plus 1 here to make sure that I begin with positive, and then I have to put a minus 1 here. Because odd numbers you can write as 2n plus 1 or 2n minus 1. right? It depends where do you want to start. If you start at 0, then you write 2n plus 1. If you start at 1, then you write 2n minus 1. Otherwise, you'll be missing the first odd number. Okay. So, okay, I like it like this. I'll keep it like that. So now we see it like this. Is it alternating? Now we can say yes. This is an alternating series. Okay? And you can spot it because, again, if you write the terms, then you should see, you should see the pattern. That if you look at the original, you should see that you will get a bunch of zeros. Then you need to understand that you ignore the zeros. And the terms that matters, they are alternating. Positive, then negative. Positive, then the next one that matters will be negative. And so on. Okay? And that's going to give you the hint. How about C?
Yes.
It is alternating, right? Because when n is even, what do you get here? A multiple of 2 pi. And what's cosine of a multiple of 2 pi?
1.
Positive 1. When n is odd, what do you have here? Negative 1. Because you're going to end up, you have a multiple of pi, an odd multiple of pi, which cosine of pi is negative 1. So you will always end up at pi in the unit circle. Okay? Which is negative 1. So this is a fancy way of writing. So the first term is positive, right? So this is a fancy way of writing this one. Yes? You understand this? So cosine of n pi is the same thing as negative 1 to the n. When n is even, you get 1. When n is odd, you get negative 1. They are the same. So, yes, this is alternating. Okay? So we are going to learn how to determine convergence of all of these series that are written down here that are alternating. The ones that are not alternating, for example, this one, what do you know about this? Converges or not? Why?
This is a harmonic series.
Okay, so it's a negative harmonic. So you will take out the negative, and then you do with the harmonic, right? The harmonic diverges, so then this one is just harmonic times the negative 1, so it has to diverge as well. Do you understand? I mean, the harmonic is with positive terms. And this is the negative harmonic, if you want, because this is really minus 1 whatever. Okay? But the others, we will be able to study it. For example, this we call this the alternating harmonic. And we're going to see that this one converges. Okay? We're going to study that immediately. In fact, all of the ones that we have here converge. Okay? Even this one. All right, so let's go for it. So do you understand what alternating series is? All right, so now, natural question is, how do we determine convergence? 122, what is this? So how do we determine convergence? Okay, and for the sake of argument, it doesn't really matter which one of the two I look at. So, for example, I'm going to be taking a look at this one, and let's assume that the first term is positive. If the first term is negative, that's okay. Just factor out a negative, and then analyze the series that has positive at the beginning and then negative, positive, negative. Okay, just to make the discussion easy. So, consider an alternating series. Let's say the sum, negative 1 to the n plus 1 of an, and let's begin at from 1 to infinity. Again, the limits here are not really too important where I begin at. But by saying this, basically, this is equal to a1 minus a2 plus a3 minus a4 plus a5 minus a6, etc. Okay, so let's say that we want to determine convergence or something like this. Of course, we need to know something about the AIs. Okay, we need to know something about the sequence AN to be able to control what's going on here. And here is the idea. We already have techniques to analyze series with positive terms. And one of the techniques that we used was that to understand Sn, we took advantage of the fact that the terms were positive. Why? Because we got a property for free. What property did we get for free?
Monotonic increase.
Monotonicity, right? Sn will always be increasing because you will always be adding a positive quantity. So the question is, can I get something like that happen here? Well, if you look at this, so consider, if you look at this, I want you to look at this, right? Because alternating, then we will always have a term minus the next one, plus a term minus the next one, and so on, yes? So if we say that we require an to be decreasing, meaning that the terms of the sequence are getting smaller and smaller, what's going to happen with these consecutive differences that we have? This will be a positive number, right? This will be positive, this will be positive, this will be positive, and then we're going to be having this quantity plus a positive quantity plus a positive quantity, and we'll be able to get the monotonicity, something similar to what we had before, okay? So that's one requirement that we're going to have. So first, we're going to assume that the sequence AN is monotonic decreasing, well, non-increasing. Monotonic non-increasing. And in other words, what I mean by that is that AN plus 1 is less than or equal than AN for all n. Okay? In other words, when you go to the next term, it's going to be smaller than the previous one. Okay? So let's assume that. Let's work with that. Secondly, notice that the plus and the minus are already taken care of by negative 1 to the n plus 1. So AN itself is positive. Okay? What do you think is going to happen if the limit of AN is a number that's not 0? First of all, if this limit is infinity, then the whole thing will diverge because of the divergence test, right? So let's say that this AN is a number. The limit of AN is a number. Let's say it's 3 for the sake of argument. What do you think is going to happen to this sequence, the original sequence, the alternating sequence, if the limit is 3? The terms of AN are getting closer and closer to 3. So because this is alternating, then the actual sequence is getting closer and closer to what? 3, negative 3. 3, negative 3. It's getting, part of it is getting close to 3 when n is even, and then when n is odd, the other part of the sequence is getting close to negative 3. What does that mean about the sequence itself?
It's getting closer to 0.
No, it diverges
Okay.
because it doesn't get close to anything. Remember our first examples of 1, 3, 1, 3, 1, 3. That doesn't converge, right? Because it doesn't get close to anything. It actually gets close to two things, to 1 and 3. Here, if AN has a limit that's not 0, what's going to happen is that the sequence negative 1 to the n plus 1 times AN, which is our general term sequence, okay? This sequence is not going to have a limit because it's going to be getting closer and closer to two values. The odd subsequence is going to get close to minus whatever the limit is, and the even subsequence is going to get close to the positive version of the limit. Do you understand this? So once again, by divergence test, this won't be equal to 0. In fact, it's not going to exist. So this won't be equal to 0, and the series diverges. So if we are hoping convergence, we already said that we want this because we'll be able to control what happens here. Second, we must require that the limit of AN by itself is 0. If the limit of AN is not 0, then what's going to happen is that this part right here is not going to have a limit, and therefore the divergence test kicks in and tells you that this diverges. Okay? So if we're hoping for convergence, we need another assumption. So we need to assume also that the limit as n approaches infinity of AN is 0. Do you understand why we did these two assumptions? Okay? Now, with this, I'm gonna try to argue to figure out whether with this condition, the question is, are these conditions enough for this series to converge? If by assuming these two things, is this enough to deduce convergence there? If we say yes, then we are in business. In fact, the answer is yes. That's called the alternating series theorem. Okay? But what we're about to do is prove. The reason why we need to prove it is because there is a consequence of this, which is called the remainder theorem for alternating series. Okay? That will allow you to estimate alternating sums. And to understand that estimate, actually, the reason why that works is hidden behind the proof of the alternating series test. So we need to prove it so we can see why that works, okay? To be able to understand remainder theorem. So anyways, given these conditions, let's go ahead and let's analyze the series. Of course, we need to consider Sn, right? So consider Sn, the sequence Sn, and we're going to study this. Our job is to deduce that this sequence must converge, okay? This is what we want to say, okay? The trick here is that because I want to make pairs like that, to be able to have positive stuff, I need to make sure that I have the right amount of terms all the time. For example, if you want to make pairs, you want to have an even amount of terms all the time. Otherwise, there will always be one guy left over, okay? So I'm going to split this sequence into two sequences. The sequence with even terms and the sequence with odd terms, okay? This, if I show that both of these sequences converge, and they converge to the same number, then this sequence must converge to the same number as well. So when you put them together, you get this, okay? It's like you have a list of numbers, you split it in two lists, but everything is in one list, either in this list or in this one, okay? You split it in two lists, and if the two lists get close to the same number, then the original list has to get close to the same number. Do you understand what I'm saying? Okay, so that's the strategy we're gonna take. So consider Sn, and note that Sn can be split as S2n and S2n plus 1. In other words, the sequence of partial sum that I always have an even amount of terms. So instead of adding one, I always add two terms, right? So the first term will be A1 plus A2. The second term in this sequence is A1 plus A2 plus A3 plus A4, and so on. Yes, I want to make sure that I always have an even amount of summats. And this one is when you have an odd amount of summats, okay? So any term in here either live in this sequence or in this sequence. Do you understand this? If you pick a term from here, it will have either an even or an odd amount of summat. If it's even, it lives here. If it's odd, it lives here. If we show that these two lists get close to the same place, then this one has to get close to the same place. Okay. All right. Now, so S2n, what is this equal to? This is equal to A1. Remember, this is alternating. Minus A2 plus A3 minus A4 plus, keeps going. Now, the last two terms are what? A2n minus 1 minus A2n. Yes? Notice that the even guys are the ones that have the negative in here. Okay? The 2, the 4, the 6, the 8, those are the terms with the negative. And the last two terms are, I need to add all the way up to A2n. That's what S2n means. So the last two terms are A2n minus 1 minus A2n. How many pairs do I have here? I'm going to put parentheses like this. How many pairs do we have here? We have n pairs. Yes? I mean, it depends on n. We have n pairs. So if n is equal to 1, you only have one pair. If n is equal to 2, it's up to here, so you have two pairs. Right? And so we have n pairs. Now, what can we say about each of these parentheses? This is greater than or equal than 0 because of the monotonicity assumption. This is greater than or equal than 0 because of the monotonicity assumption, and so on. So that means S to n, every time that you look at the next term, you're always adding a positive quantity. So what can we say about this? It's monotonic, right? So S to n is monotonic, non-decreasing. Yes? So we know that as n gets bigger and bigger, S to n is going to get larger as well because we're always adding positive quantities. Do you understand this? For example, this is S2. This part right here is S4. The S to n is made out of S2, S4, S6, S8, etc. So S2 is going to be less than S4 because S4 is this plus this, and these are positive numbers. Okay? Then that's less than S6 because S6 you add an extra positive parenthesis and so on and so forth. So it's monotonic. Remember, I want to show convergence. So what else do we need to argue? That is bounded. So let's try to bound this. Okay? Now here's the trick. If we want to bound this, here is what I'm going to do. Now note S2n is going to be equal to the following. So what I'm going to do is, I'm going to leave A1 alone, and I'm going to factor out a negative. So, okay, let me rewrite what I have here. So we have this. Let me write the last three, the last four. So the last pair is 2n with the 2n minus 1. That was positive. Then comes the 2n minus 2, and then comes the 2n minus 3. Those are the last four. That's the tail of this, right? 2n, 3, 1, 3, 3. Okay, so what I'm going to do now is I'm going to leave A1 alone. And I'm going to factor out a negative. Now, I want you to understand that when I do that, I'm going to be making pairs. So, because I'm leaving this guy alone, then I'm going to be pairing this with this with the next one, and so on and so forth. So this one will get paired with this one, and this one will be alone as well. Okay. So I'm going to have this left over outside here, and then inside this parenthesis, because I took out a negative, the sign is going to change, right? Instead of being minus, looking here, minus, plus, it will be plus, minus. Yes? So this A2 minus A3 plus A4 minus A5 plus all the way up to, and then the last two, that would be A2n minus 2 minus A2n minus 1. So this last pair, the sign changes. And as we did earlier, I'm going to make pairs here. I have 2n minus 1. I have n minus 1 pairs in here. Okay? Moral of the story. Why did I do all of this? What do you know about this parenthesis? It's positive because remember, we have monotonicity. A3 is less than A2, right? So when you do A2 minus A3, that's positive. The next parenthesis is also positive, and so on and so forth. That's positive. So this whole parenthesis is positive. Yes? So what do we have here? We have A1, and then we are subtracting a positive number minus another positive number. So all of this is actually less than or equal than A1. Yes? So S2n is less than or equal than A1. Take a second to digest this. So I mean, I played this game because I want to show that if you leave the first guy alone, the rest of the stuff is actually a negative number. If I now factor out a big negative, I have minus something positive because, minus this. So you have A1 and then you're subtracting positive stuff from it. Do you see what I'm saying? Mm-hmm. So if you have a 5 and I subtract a 3 and a 1, I get something less than 5, right? I get 1. So that's what's going on. You have A1, I subtract a positive quantity, and then I subtract another positive quantity. So all of this, which is S2n, is less than or equal than A1. A1 is bigger. If you're doing A1 minus positive stuff. Yes?
So that's not.
So it's bounded. It's bounded. I mean, it's monotonic, and it's bounded. So what can you deduce about S2n? Convergence. So it means that the sequence S2n is bounded. So it converges. So it converges. In other words, the limit as n approaches infinity of S to n is going to be equal to something. I'm going to call it L1. Okay? Let's call it L1. I need to play the same game with the other one. Okay? Remember, this is half of the sequence that we want. Okay? This is the sequence of even terms. Now we're going to do the same thing with the odd terms. Okay? The point is that the same sort of trick is going to work. Okay? Yes?
So above we said it's monotonic and non-decreasing.
Yes.
And here, now it is decreasing because we're subtracting positive numbers, right?
No. I'm comparing with A1. The sequence itself is non-decreasing. Look at the original one. Okay. All I'm doing is I did this just to show you that whatever we get, it will never be bigger than the first term. Yeah, the frequency is getting bigger, but it's not gonna be more than the first term.
I see.
Okay, that's what we just argued here. Do you understand? Okay, let's play the same game with 2n plus 1. Now, s2n plus 1, what is this? This is a1 minus a2 plus a3 minus a4, and we're to end up with an odd guy. So keep going. What's the last pair? That would be a2n minus. Okay, so the pair itself will be 2n minus 1 minus a2n, and then plus a2n plus 1, like that. Remember, the negative is always, when we don't put parentheses or we don't factor anything, the negative is always with the even guy. That's how s2n plus 1 looks like. And, okay, so let's play the same game. I put parentheses like this. Once again, monotonicity, right? Positive, positive, positive. And this guy itself is positive, right? So, because s2n plus 1, we're just adding positive stuff every single time, right? Because remember, now, if you move the next one, you just need to throw in an extra pair here, okay? The even and the odd, the even and the odd. And you're just adding positive stuff. So, s2n plus 1 is monotonic. Non-decreasing. Do you understand this? Now let's play the same game. I want to show that it's bounded. So I'm gonna have my a1. I'm gonna factor out the negative. But this time, if I separate this, now I have an even amount with everybody. So there won't be any left over at the end, right? Because take out the first one. This is an odd number of terms. You take the first one, you have now an even number. Okay? So we have nice pairs now. So we have a2 minus a3 plus a4 minus a5 and so on. And then the last pair would be a2n minus a2n plus 1. And then, of course, I'm going to place parentheses like this, right? Making my pairs. What do we know about each parenthesis? I want you to notice how heavily we're using the assumption that this is non-decreasing, non-increasing, that the terms are getting smaller and smaller, right? We're heavily relying on that. If we don't make this assumption at the beginning, we have no control of what's going on here, so we cannot do these arguments, okay? That's why this assumption is important. You see why this one was important, because otherwise it would diverge because of the divergence test, right? But this one, the first one, is the one that allows to control Sn somehow. So this is positive, not negative, not negative. So once again, this entire parenthesis is a positive quantity. Yes? So that means that we have a1 minus something positive. Moral of the story, this is less than or equal than a1. So once again, it's bounded. So s2n plus 1 is bounded. Yes? So it converges. So it converges. So let's say that the limit as n approaches infinity of s2n plus 1 equals, let's say it equals to L2. Okay? Okay, so we have our two lists, and they're both getting close to something. The list of even guys is going towards L1. The list of odd guys is going towards L2. Yes? Now we have to make sure that L1 and L2 are the same number. Because if we show that L1 equals L2, then that means the whole list converges and goes towards that number. Okay? So that's what we need to argue now. Question? Is L1 equals to L2? Well, let's answer the question. Again, I'm doing it, I'm not pausing for you to try to answer it, otherwise our time is going to run out, okay? So I just want you to see the story. So, is L1 the same as L2? Well, here you have to think about something else, and the something else is the following. What is this? Now here I want you to answer my question. What is this equal to?
AN, just AN.
Almost. Look what S2n plus 1 was. S2n plus 1 is the sum all the time, right? If you ignore this part, what is this? S2n, right? So if you do S2n plus 1 minus S2n, you're basically removing this part, so you get H2n plus 1. Yes? It's just like Sn minus 1, you get An, but here you get A2n plus 1. Yes? So that's the observation. That you get here A2n plus 1. And now we're going to use this. Okay? We assume that the sequence An goes to 0, right? What can you say about the subsequence A2n plus 1? That's a sublist of the bigger list. If the entire list goes to 0, gets closer and closer to 0, what happens if you look at the odd spots of the list? Does it get closer and closer to 0? Yes, of course. Otherwise, the list itself will not be getting close to 0, right? We're saying that the whole thing is close to 0, so the odd spots, they have to get close to 0 as well. Yes? So the fact that this one is 0 implies that this is also 0. So notice that this approaches 0 as n approaches infinity, since the original sequence approaches 0 as well. Does that make sense? So, limit as n approaches infinity of S2n plus 1 minus S2n equals 0, right? But remember, the limit of the difference is the difference of the limits if the limits exist. Now, we just argue that these two guys converge, so they both have a limit, right? So this is going to be equal to the limit of this guy minus the limit of this guy, and that difference must be 0. But this, we call this one L2, we call this one L1, so that means that L2 equals L1. Okay? So now we can argue that because the two sublists converge and they converge to the same place, the original list has to converge to the same place. So the sequence Sn converges as well to whatever this L1 equal to L2 is. Okay? Moral of the story, what we have here is alternating series test. So when you have an alternating series, you need to make sure that the terms An, so when you take, and you do that by making everybody positive. So you take absolute value of this and you get An, okay? So when you look at the term An, it has to be monotonic, non-increasing, and moreover, you need to verify that the limit is 0. If those conditions are satisfied, your series converges. Okay? That's what, because that was the only thing that we needed to guarantee convergence, as you saw in the proof. Okay? For example, in all of these things, as this converges, well, this is my An, 1 over n, the limit is 0, and it's decreasing, converges, by alternating series test. This one right here. This one was, the hard part of this one is that you need to understand that this is the same as this, okay? But once you understand that, then alternating, good, then you look at this expression, the limit is 0, and this is certainly decreasing, converges, okay? And same thing here. This is your An, because this part is the plus minus, this is your An, the limit is 0, and decreasing, converges. Do you understand? This is pretty easy to use alternating series test, okay? You just need to use those two conditions. Those two. So let me write it down. So we have a theorem, and the proof is what we just did above. This is called the alternating series test, so this should go in your list of statements or theorems. So alternating series test. and it says let AN be a positive sequence, then the alternating series sum from 1 to infinity, -1 to the n AN, and sum from 1 to infinity. In other words, it doesn't matter whether you just start with a positive or a negative. You can adapt the argument that we did if the first guy was negative instead of positive. Okay, it's not really a big deal. Just factor out minus and that's it. Okay. So that's what I mean here. This is the case when it begins with negative stuff, and this is the case when it begins with positive stuff. Okay, that's what I mean. So then this series converge, and this series converge if the following conditions are satisfied. If the following conditions are satisfied. Okay, so who can tell me what are the conditions? Number one,
Monotonic, non-increasing.
the sequence AN is monotonic, non-increasing, exactly, the terms get smaller. Hopefully you see that this was heavily used in our discussion, okay? To guarantee those parentheses to be positive, it was heavily used, this property. And number two, what's the other condition?
The limit of the series converges to 0.
The limit of AN must be 0. Why do we need this?
Because if not, then you can't do the last part of the term, whether they're bounded, the bounds meet the same way, or if the top and the bottom converge at the same
The two limits are equal, and let's say that is decreasing, but then you, for some reason, you argue that the limit is 1. That means this does not apply. You cannot use this because one of the conditions are not satisfied. However, what could you do in that case?
They would diverge.
Why it would diverge? Because you use divergence test. Using divergence test, you can argue that then the alternating series would be alternating, the sequence would be alternating between the positive and the negative number of the time, getting close to those two, so the limit does not exist. So the alternating series test will not apply. If any of these conditions are violated, the alternating series test does not apply. Okay? But if this one in particular is violated, then you can use the divergence test to argue. Okay? So let's keep that in mind. All right. Questions? Do you understand the statement? It's actually pretty simple to check. Okay? Just ignore make sure that it's alternating. Once you convince yourself that it's alternating, then you ignore the -1 to the n part and just look at the sequence AN itself, the positive version of the terms, and you need to check these two conditions. That's why we did 5.1 at the beginning, because at the end of the day, this goes back to starting sequences. You need to guarantee monotonicity and make sure that the limit is 0. That happens, converge. Okay, so yes, example. I mean, we already did a bunch of examples above, but let me just write down a few. Let's say the sum from 1 to infinity of -1 to the n plus 1 of 1 over n. So what can we say about this one? Converges or diverges? So here, notice that we have AN. What's AN here? 1 over n. So first of all, you clearly recognize this as an alternating series, right? Then you have to look at AN, that's 1 over n, and then you need to check two things. I'm gonna do this one because this one is kind of easier to do. So when you take the limit, we certainly get 0, so as a check. And then second, do you understand that this is monotonic? So certainly 1 over n is always greater than or equal to 1 over n plus 1, right? If you look at 1 over n plus 1, it just gets more for all n. So that means AN is not equal than AN plus 1. So AN is monotonic, non-increasing. In fact, it's decreasing. So everything is, all the conditions are set. So we can say that by the alternating series test, I'm gonna be calling this AST. By the alternating series test, the series converges. Do you understand this? Yes? Okay. How about this one? Let me do another one. How about this guy? Is it alternating?
Yes.
Yes. So what's our AN?
N plus 1 over N.
N plus 1 over N. So this, we know it's alternating, so let's check our conditions. So I always like to check the limit first, okay? So if we take the limit of AN, what do we get? What is the limit?
1.
1, right? Point is different than 0.
So it doesn't-
So, well, it tells you that the alternating series test is does not apply. Okay? You cannot use alternating series test. However, by the discussion that we had, we know that when this happens, then when you look at the original series, the original sequence with the negative 1 to the n plus 1, because this gets close to 1, then the original 1 is going to get close to either 1 or negative 1, right? So then the limit itself is not going to exist. So by the divergence test, the series diverges. Okay? But not because of alternating series test. Alternating series test does not apply. But from here it follows that negative 1 to the n plus 1 approaches both 1 and negative 1. So the limit does not exist because it gets close to 2 different values, and therefore we can use now divergence test. The limit does not exist. So by the divergence test, the series diverges. So here we use divergence test. We didn't use limit comparison, alternating series test. Okay. Do you understand this? Okay. So 4 minutes. Okay. Yes.
Quick question, would you still recommend us to always use the divergence test before this, before using the alternating series test?
I mean, alternating series test is super easy. So if you see that it's alternating, just go straight to the alternating series test.
Oh,
And because you need to check 2 points, you need to check the limit anyway, just do the limit at the beginning. If you don't get 0, now you know that you can say it diverges, not because of alternating series test, but then you know that the divergence test will tell you the answer. Right? If you see it's alternating, just go for it. Okay? Now, let's look at number 1. I'm going to introduce another notion to you. Let's look at number 1. This series converges, right? Now, what happens if I take absolute value? If I look at the series of absolute value, by taking absolute values of all the terms and making everybody positive, right? What happens? It diverges because you get harmonic, right? So whenever this happens, we say that this series, we have a term for that, we say that this series converges conditionally. So conditional convergence means that the series converges, but when you look at the absolute value of the terms, by making everybody positive, the series diverges. Okay? That's called conditional convergence. Now, when you take absolute value and the series converges as well, we call that absolute convergence. Okay? For example, let's see, what do you think about this one? Does this converge or diverges? This one clearly converges, right? By the alternating series test, so it's very easy to see. 1 over n squared, the limit is 0 and it's decreasing, so it converges. But now when we take absolute value, what happens? We get 1 over n squared, which is converging. So the convergence here is stronger than the one above. We say that this converges absolutely. This is absolute convergence. That's what I'm about to write now. So, and then the theorem is that if a series converges absolutely, then the series itself must converge. In other words, if the series of absolute value converges, then the series itself converges. And that's how we're going to deal with series that are not alternating. Let's say that you have a series that's behaving crazy. Sometimes it's positive, sometimes it's negative, and so on. Well, we're going to take absolute value. We're going to make everybody positive. And then we can use comparison, limit comparison, all the stuff that we know. If that converges, then the original series will converge. Okay? So that's important. For example, this will allow us to deal with this kind of stuff. If you have the series, this series is not always positive because sign, as you know, it oscillates, right? But it's not alternating either because the sign is sometimes is positive as long as n is in quadrant 1, then it's sometimes negative, well, quadrant 1 and 2, then it's sometimes negative, quadrant 3 and 4, then positive again sometime, then negative again sometime, right? So it's not really alternating, but if you look at absolute value, this is going to be bounded by making absolute value is positive, and then it's going to be bounded by 1 over n squared, which converges. Therefore, direct comparison test tells you the absolute value version of this converges. So this one converges absolutely. If this converges absolutely, then the series itself converges. Okay. So that's what we want to do. That's how we're going to control series where the terms behave irregularly, sometimes positive, sometimes negative. Okay. And I guess I will write that down next time. And now you know, because when you're doing the homework, there will be questions about absolute or conditional convergence. You either look at the book to be able to answer those questions, so you don't have to wait until Thursday to answer those questions, okay? But it's basically that. Absolute convergence means that when you take absolute value here, the series that you get still converges, okay? Conditional convergence means that the series converges, but when you do absolute value, it does not converge. Just think about the alternating harmonic. That's your classic example, okay? So next time, I will write these definitions. I'm gonna talk about the error remainder theorem, which basically says that when you cut the series at a point and you approximate with the partial sum, the error that you make is bounded by the next neglected term. And it follows because of this. Notice how here, the first term is actually an upper bound for the series of partial sums, right? So if I cut the sum at this point, the next term that I'm ignoring is gonna be bigger than everything else, than the sum of everything else, because of the same idea. That's what the error remainder theorem says, okay? There are problems about that in the homework. So if you wanna do your homework before Thursday, read the book so you can do those problems. If not, you will need to wait until Thursday. I'm saying this because the exam is on Tuesday. You don't wanna wait until Thursday to understand this topic, okay? So be smart when you start. All right.
So, I want to ask, is there any way that if it's non-decreasing, would it also converge? Because if you group it like this instead, then since it's increasing, this will stay positive and it'll stay positive. And then I started trying to do the proof with it, but then I got confused.
So you said if it's monotonic,
Non-decreasing.
non-decreasing. Okay, so let's think about it for a second, right? The limit has to be 0, right? So if an is monotonic non-decreasing, I mean, how is it possible to have a sequence?
I don't know, that's why I was asking.
No, it's not, what I'm telling you is not possible because an is positive, because we're already determining the negative 1 to the n is what gives it positive, negative, positive, negative. An itself is positive. Now, we know the limit has to be 0, but now if we say that the terms don't go down, they either stay the same or they go up, there is no way. If you have something positive, it either stays positive or it becomes bigger, right? If we say that it's non-decreasing. So there is no way it's going to get close to 0. It's going to go away from 0. And so when you do the alternating behavior, divergence test kicks in and it diverges. So yeah, so basically by requiring that the limit must be 0, we are saying that if we have any chance of getting this to work, our sequence must be non-increasing. Yeah. So now you know also that if this is the condition that fails, it also diverges. Why? Because you use the divergence test. Because if this condition fails, this is not going to happen. You're gonna get something else.
Automatic failure down the line.
Yeah. So divergence test. A good question.
How, because I'm still used to doing it analog. How would I send you the appointment timing, like the blue slip? Do you just want me to bring in the blue slip on Thursday, or? I
Take a
still
picture.
never email them. Just take a picture of it.
Take a picture and
attach
send
to
it
an
to me.
email.
And send it
Okay,
to me.
thank
Yeah.
Thank you.
All right.
I'm so used to all this, doing it all analog. Much as I stayed on the computer most of the time, I'm used to everything still being analog. Like, I don't even think I've ever used a car wash. I just wash it all by hand on Fridays, like my dad taught me,
Oh,
etc.
I see. All right,
Thank you.
you're welcome.